Hello everyone, welcome to the session. Here I am going to discuss about electrical machine subject, and in this session I will be discussing about introduction and some basic concepts behind the electrical machines. Okay, before moving on to the session, let me introduce about myself. My name is Naveen. I have around 11 plus years of experience in teaching. Most of the times I will be teaching electrical machines, networks and measurements too. And I will try to bring those networks basics into the machinery, and I will try to bring the measuring instruments topics into the machinery while I am teaching the electrical machinery subject. Okay, because I don't find much big difference between measuring instruments and electrical machinery, because measuring instrument is a small size motor, and whereas electrical machinery is a bigger size. That's it. Of course, the scale and all those things are going to be same. Anyhow, keeping it as a side. So coming to the syllabus, let me introduce some syllabus, especially gate oriented syllabus and engineering service examination oriented syllabus. The syllabus is like this. If you look at the syllabus, there are different parts are there. There are different parts are there. One, transformer. Of course, he has given single phase transformer and three phase transformers, and then later DC machines, three phase induction machines. By the way, he has given single phase induction machines also. In the three phase induction machine itself, he has given single phase induction machines also. And the next one, synchronous machines. Okay, this is the gate syllabus. So I can divide the entire machinery into four parts. One as transformer, and the second one is going to be DC machine, and third one is going to be induction machine, and fourth one is going to be synchronous machine. Even you see the engineering service examination syllabus also, it looks the same. If you see, again the same parts, transformers and DC machines, induction machines and synchronous machines. So these are the four parts you need to cover to complete the electrical machinery subject. Okay, there is a small difference between gate syllabus and engineering service examination syllabus. In engineering service examination, there will be an extra syllabus of special machines like stepper motor, servo motor, reluctance motor, or hysteresis motor. These kind of small size portable machines are there, no? So you'll be having some extra questions on these special type of machines in the engineering service examination. Coming to the weightage of electrical machines, in the gate examination weightage is around going to be minimum of 8 marks and maximum it can touch up to 10 marks also. I am just giving on an average figure. Minimum 8 marks will be there and maximum it can touch up to 12 marks also, but I am giving 8 to 10. And coming to engineering service examination, it will be around, you will be getting around 10 to 15 questions. Sometimes it will be 10 questions, sometimes it will be 17 questions also. So number of questions varies from 10 questions to 15 questions, and each question carries 2 marks. Each question carries 2 marks. So I can say minimum of 20 marks weightage will be there and maximum of 30 marks weightage will be there. So whether you take gate examination or engineering service examination, the weightage is a very huge weightage. And even you take the state government public sector examinations like electricity board, whatever the electricity board, the state government examination, Kerala electricity board examination will be there, no? So for that also the weightage is a good weightage according to the core subject of machines. I don't find much bigger difference between power system weightage and machine weightage also. It's almost same. Huge weightage will be there. All right. So this is the syllabus of gate and engineering services examination. Let me tell you some important topics in the electrical machinery. Okay, I did not tell you exactly what are the topics which are existed in the entire machinery. So let me write here whether it is gate or engineering service examination, or any public sector undertaking companies, including state electricity board examinations also, right? So these are the important topics you need to concentrate. These are the important topics you need to concentrate. So let me write here, the first topic is transformers. As I said, the total electrical machinery subject is divided into 4 parts, and I am repeating once again: transformer, DC machines, induction machines and synchronous machines. So in the first part, in the transformer, what are the very important areas? From those areas, every year there will be question in engineering service examination as well as gate examination, and even those topics are very important for state electricity board examination, state public service commission examination also. Okay, so let me write some topics here. Let me show you some topics here under the transformer. If you look at transformer, the very important topics are here: operation of transformer on load, operation of transformer on load. Okay, so this is one important, and in this area they'll ask you the question like this: if certain amount of load is placed on the transformer, like resistance load, inductance load or RL load, what will be the source component of current, or what will be the primary component of current? That kind of questions they'll ask you. Or else during the load we will be getting an equivalent circuit, right? So I am writing here itself, and equivalent circuit of the transformer, equivalent circuit of the transformer during the load. Okay, so you will be having secondary winding components, load impedance, primary winding components and the no load branch impedance, that is core branch impedance. So the question will be on load or otherwise the equivalent circuit during the load. Okay, this is very important question. Like when you transfer secondary parameters to source side, what will be the changes in winding parameters? Will it be divided with k square or will it be multiplied with k square? That kind of questions also you can expect as 1 mark, sometimes 2 marks also. And another topic is here, after the operation, the very important topic is losses in the transformer, We have majorly 2 losses, one is iron loss, another one is copper loss. Here the question will be on iron losses. We know the iron losses parts as hysteresis loss and eddy current loss. Okay, hysteresis loss and eddy current losses together we call them as iron losses, or otherwise constant losses or core losses. Now the question will be on this area. How do they ask? They will give you a transformer with a rating of 200 volts 50 hertz, and they will ask you, if the transformer is designed at 200 volts 50 hertz and now if I am supplying 230 volts 60 hertz, if I change the voltage applied and frequency applied, what happens to the hysteresis losses and eddy current losses? If I keep the voltage as constant, if I change the frequency, what happens to hysteresis losses and eddy current losses? This is very important area for all the competitive examination. Okay, and after this losses, I can tell you one more area, that is, during classes itself we will be discussing about testing. Okay, and after this, the one more important area is regulation of transformer. The voltage regulation of transformer. It is similar to transmission line voltage regulation itself. Okay, they'll ask you, they'll give you some resistance, reactance parameter, they'll give you some load. At what value of load the regulation is maximum, at what value of load the regulation is minimum, or otherwise at what value of power factor the regulation is maximum. That kind of questions they'll ask you. Okay, and after this regulation, one more important area is efficiency of the transformer. Efficiency of the transformer. This is very important, because 2 marks question can be asked from this area, efficiency of a transformer. They'll give you some information about the kVA rating, load value and power factor, and they'll ask you what will be the efficiency of the transformer when the copper losses are this much, when the iron losses are this much. That kind of questions you can expect. or at what value of load maximum efficiency takes place. That kind of question also you can expect. After the efficiency, these are the common topics for whether it is single phase transformer or three phase transformer. It's same, operation is same, principle is same, everything is same. The only thing is in three phase transformer you will be having two extra windings, two other extra phases. That's it. Okay, right. So I don't say much difference between these topics whether it is a single phase transformer or three phase transformer, it will be same. All right, but there is one topic called vector grouping. Vector grouping. This vector grouping comes under three phase transformers. Vector grouping comes under three phase transformers. Okay, it's like if you have star-star connection, what is the phase displacement between primary and secondary? If you have a star-delta connection, what is the phase displacement between primary and secondary? That kind of questions they'll ask you. Okay, so if star-star is having 0 degrees phase displacement, delta-delta is having 0 degrees phase displacement, these two transformer comes under one group. Okay, if delta star is having one displacement, star delta is having one displacement, then delta star, star delta comes under another grouping. That's what vector grouping, where we will be discussing about phase displacements of the transformer. So these are the important areas. These are the important areas in the transformer topic. And coming to the next one, after this I can tell you the second part. I'll be taking it as induction motor or induction machine. Induction motor or induction machines. Okay, right. Generally machine is nothing but or it can be a motor or it can be a generator. You can operate it as a motor, you can operate it as a generator. Here most of the discussion is with respect to motor only. Okay, here that means what in the syllabus we will be discussing more than 95% of discussion is with respect to induction motors but not induction generators, because induction generators are not much popular because of variable frequency of output. Now coming to the induction motor, the subtopics I can list out as, here I can say equivalent circuit of the induction machine. So they will be giving you rotor side parameters, they will be giving you stator side parameters, maybe sometimes they will be giving you all the parameters referred to the stator side, and they will asking you to calculate starting current value, maximum current value, or otherwise full load current value. Okay, based on this one, we have one more topic that is called power flow in induction motor. Power flow in induction motor. It's like how the power is transferred from stator to rotor, and the power division, we'll be discussing about power division. After the rotor is receiving the power, in what forms it is going to be lost and how it is going to be transformed at each and every stage we'll be discussing. It's like gross mechanical power developed, rotor losses, air gap power or rotor input, stator losses, stator input, that kind of power divisions will be there. The question can be asked at any point. What will be the rotor copper losses if rotor input is this much and shaft output is this much, by giving the mechanical losses. So this is one more important area. After this, the very important area is torque slip equations and characteristics. Torque slip equations and characteristics. This is very important area. Every year one question will be there in the gate examination. Okay, torque slip equations and characteristics. Every year one question will be there. They will be asking about starting torque value or maximum torque value, full load torque value, or else slip corresponding to starting, slip corresponding to maximum torque, slip corresponding to full load torque, and the speeds corresponding to full load, speeds corresponding to maximum torque. Many questions are there in this topic, in this subtopic. Okay, at what value of resistance maximum torque takes place? Okay, right, that what is the value of, what is the external resistance you need to place in the rotor circuit to get maximum torque, condition for maximum torque, that kind of so many questions are there in one equation. So every year there is a possibility to get question from this area, whether it is GATE examination or engineering service examination. You take any examination in that particular calendar year, one question definitely will be there, whether it is 1 mark or 2 marks. And after this one, after this torque slip equations or torque slip characteristics, there is one more important area in the induction machines, that is speed control. This is speed control of induction motors. We can control the speed of a motor. Don't try to control the speed of a generator, because generator input is mechanical energy. Don't try to control the speed of the generator, because we generally test the output. We generally test the output. We will be giving some amount of input and we will try to test the output, whether we are getting required output or not. We are discussing about motor here. So motor input is electrical energy. Motor output is what? Mechanical energy. So I want to test the motor output. Output is what? Maybe electromagnetic torque or otherwise speed. So I am testing this speed control. I just wanted to test the performance of the motor. Okay, so speed control can be done according to the application, whether the application is constant torque load or constant power load. According to that, we will be testing. So these are the 3 to 4 important areas in the induction machine area. Of course, the speed control can be done from stator side or rotor side. All the types we will be discussing in detail when it comes to each and every topic. If I go ahead with the next one, the next machine is going to be DC machines. As I said earlier, machine can be motor or generator. Machine can be motor or generator, right? In the induction machines, we have more concentration on motor itself, not on generator. But when it comes to DC machines, we have equal importance on motors as well as generators also. We have equal importance on motor as well as generator, and the important topics will be, they will be asking about EMF equation questions. Okay, it's like back EMF is equals to supply voltage minus armature resistance drop, or otherwise generated EMF is equals to terminal voltage plus armature resistance drop. The EMF equation questions. Okay, so voltage equations of motor and generator. Voltage equations of motor and generator. Similarly, after this, characteristics of motor and generator. Characteristics of motor and generator. So they will be asking motor characteristics or otherwise generator characteristics. Sometimes graph based questions also you can expect. Speed versus armature current characteristics, torque versus armature current characteristics of motor, any motor, maybe shunt motor or series motor, compound motor, they will give you. Similarly, generator also, maybe external load characteristics, internal characteristics or no load characteristics, they will be asking you to answer. Okay, right. So if you look at the other one, in the DC machines, the very important area is another one, that is speed control of motors. Speed control of motors. Speed control of motors. I am writing here motor. Okay, this straight line symbol is DC symbol. In a circle, M and straight line symbol is a motor, DC motor. Okay, maybe armature voltage control technique, flux control technique we will be discussing here. It is very important, right? He will be giving a constant torque load or variable torque load, and he will ask you to calculate what is the speed or what is the amount of resistance required to get this amount of speed, or otherwise no load speed, full load speed information they will ask. And the last one is here, armature reaction. There are questions on armature reaction as well as some questions on, there will be questions on armature reaction. The armature reaction questions can be maybe theory oriented questions will be there, and problematic oriented questions also will be there. It's like demagnetizing effect of armature reaction, cross magnetizing effect of armature reaction, and they'll ask you what are the amount of demagnetizing ampere turns, what are the amount of number of cross magnetizing ampere turns. they'll ask you. So it's like ampere turns, demagnetizing ampere turns, cross magnetizing ampere turns, that kind of questions they'll ask you. So these are some 3 to 4 important topics on the 3 to 4 important topics coming to the DC machines part. Okay, so let me erase this part and let me rewrite this one. This is voltage equations of motor and generator. So these are 4 important parts I can list out in the DC machine. And coming to the other part, that is 4th part, synchronous machines. Synchronous machines. Here also in this part also we will be having more discussion towards generator. We have less discussion towards motor. More discussion on generator itself, same as like induction machine, we have more discussion, more than 95% of discussion is with respect to induction motor, and in the synchronous machine we will be having more than 90% of discussion with respect to synchronous generator, but not synchronous motor, because the only thing is the synchronous motor applications are limited. Synchronous generator is very, very important, because without synchronous generator you cannot generate the voltage at the power stations. So we will be having more discussion about with respect to this synchronous machines, and here the very important topics are problems on KD, KP, pitch factor and distribution factor of the armature windings. Okay, so this is one important area, and another one area is regulation of alternator. Regulation of alternator. We did the regulation topic even in the transformer also. So theoretically there is no much big difference. The formula wise as difference will be there for the alternator voltage regulation and transformer regulation. The theory is same. Okay, right. As it is we are discussing much more, we are discussing about generator. So generator output is what? Generator output is voltage. So you need to test the voltage, whether the output is good amount of voltage, rated voltage, or less than the rated voltage, or greater than the rated voltage. You need to test it. So that for that purpose regulation is we regulation as like a performance index. After the regulation, there is one important area called power flow. Power flow. Power flow, I am writing power flow in synchronous machines, that is synchronous generator and synchronous motor also. Synchronous generator and synchronous motor. I applied it as sinusoidal sign for the generator and even for the motor. So they will be asking you to calculate active power flow, reactive power flow delivered by the generator or absorbed by the motor, reactive power delivered by the motor or absorbed by the generator. This kind of questions will be there. Very important area when it comes to synchronous generator. Every time, every year one question will be there in the gate examination. Okay. After this power flow, there is one important area, that is parallel operation of generator. Parallel operation of synchronous generator. Even in the transformer also I can list out the parallel operation. Here in the vector groups only I can write out. In the vector groups only I can write out here parallel operation of generator. Sorry, parallel operation of transformer. Okay. Even in the transformers also you can have, transformer is like a generator because secondary winding is delivering the energy to the load, right. So transformer is like a generator, static generator, right. So here also parallel operation of generators, parallel operation of generators. Okay. So these are the 3 to 4 important topics I can say. These are the 3 to 4 important topics I can list out in each and every machine. So I hope the syllabus is clear to you on which part you need to concentrate more. I am not saying that I am going to take up only these topics. I am saying that these are very, very, very important topics. I wanted to write very important topics. Whatever may be the exam, these are the very important topics. Okay, I am repeating again and again. Please concentrate more on these areas, and most of the areas, whatever the areas I have represented here, I have given here, most of the areas are problematic oriented. Okay, so you need to practice a lot if you want to gain more marks and if you want to score high marks. Okay, Right. So that's introduction to the syllabus part and the very important topics I can say. And moving on to the next step, that is moving ahead, textbooks. So I just wanted to give you a quick reference for you. Whatever may be the textbook, it will give you a good information. But I prefer, if you are planning for GATE examination, I prefer Nagraj and Kothari sir textbook is good. For GATE, this textbook is good. Okay. So whatever the concise information, enough information and few solved problems are there. So if you can read it and solve it, that's enough. You'll get an idea. And if you want more practice, then P.S. Bimra, this textbook is good for GATE as well as ESE. This textbook is good for GATE as well as ESE. More number of problems are there. Compared to I.J. Nagraj and Kothari sir textbook, this textbook has many problems. So if you want to practice a lot, then this textbook is better. And the other two books are, that is Electrical Machinery by Fitzgerald or otherwise Electrical Machinery by Stephen Chapman. These two books. This book is very good theory oriented, the easy language, and you can easily connect with this textbook. Okay. So theory purpose, I can suggest this one. Theory purpose, some concepts are very well, they have explained in a very well manner. Okay. And coming to the other part, the other textbook, this is a good one theory wise, but problems are very less. Okay. You can have any one textbook, all the textbooks are available in the Google, you can just download. Okay. Alright. So these are some information about the textbooks, and moving on to the part, that is introduction to the electrical machines. Let me show you first that the machineries, whatever the machines I have listed out so far, transformer, induction machines, DC machines and synchronous machines. Let me show you the diagrams of those machines or pictures of those machines, so you will get an idea. Please try to observe. This is the diagram or the schematic picture of a transformer. So if you look at the transformer, you can find out a magnetic path or core. On the magnetic path, we have placed windings on this side and of course winding on the other side. So I can list out here physically if you look at the transformer, you can list out two things. One is magnetic path and the second one is windings. Okay. So these are the two parts you can list out. You can observe by looking at the transformer. I am not getting into each and every part and all those things. Majorly physically you can see magnetic path and windings. If you see the other machine, that is induction machine. If you see the induction machine, this is a stationary part, and in the stationary part also we have a core, and in the core we have windings. Similarly, the other part is rotating part. The rotating part is also a magnetic path. Of course, on the shaft you have magnetic path, and on the magnetic path we will be placing the slots, and inside the slots you will be having winding. So again here also I can say stationary winding, rotating winding, stationary core, rotating core. So I can write here again as magnetic path and winding. Magnetic path and windings. Okay, let me rewrite this one. So this is what I want to say. Let me repeat once again. Stationary magnetic path is there, rotating magnetic path is there. On the magnetic path we are placing the winding here and there as well. Okay, right. Now moving on to the next machine. If you see this machine, this is a DC machine construction. This is a DC machine construction. And even you look at the DC machine construction, we have projected poles. On each and every pole winding is wounded. On each and every pole winding is wounded, and the projected pole part is called as stationary part. You can take up it as a magnetic path. All right. On that we have a winding, and similarly the circular cylindrical shape a rotating part, and we call it as armature core, and on the armature core we have windings here. The armature core we have windings here. See this part, dots. These two dots are there, no? These are windings. So what I am trying to say again is, we have magnetic path on the stationary part. Of course, on the rotating part is also a magnetic path, and both on both the parts you have windings. So I can list out again here magnetic path and windings. Okay. Similarly, if you go ahead with the synchronous machine, the outer cylindrical area is stationary part, and on the stationary part we have slots. Inside the slots we'll be placing the winding. Similarly, if you look at the rotating part, on the rotor surface we have projected some poles. Okay, on the poles we have winding. Even rotor surface or rotor core is also a magnetic path. Rotor is also a magnetic path. Stator magnetic path, rotor magnetic path. On the stator also you have winding, on the rotor also you have winding. So again I am listing out here the major parts I can see are magnetic path and windings. Okay. So these are four machineries, that is what I can say, synchronous machine and DC machine and induction machines and transformer. So whatever the machine you see, whatever the machine you observe, what I can conclude is, by looking at the machines are designed with the help of magnetic path and windings. That is the point I wanted to say. Now if you know the functions of each and every machine, what actually the transformer will do, what actually the DC machine will do, and induction machine and synchronous machine, what they will do, functions. Let it be any function. If you give the transformer, for a transformer if you give an electrical energy, it will transfer the electrical energy from one side to another side, maybe electric power from one side to another side. It can transfer the power from one side to another side, electrical energy. Input is electrical energy, output is also electrical energy. Alright. If you look at induction machines, we will be giving the input to the induction machine as electrical energy, and it will be converted into mechanical energy. Okay. If the input is electrical energy, it will convert into mechanical energy. Or if you give the input as mechanical energy, if you rotate the rotor in the presence of magnetic field, it will convert into electrical energy. Whether it is motoring mode or generating mode, the construction does not change. These parts does not change. Even you see the DC machine construction also. You give the input here, electrical input, DC input. Okay, so it will convert the electrical energy into mechanical energy, or else you give the input mechanical energy to the rotor, rotate the rotor in the presence of magnetic field, it will convert the mechanical energy into electrical energy. Construction is not going to be different, whether it is a motor construction or generator construction, these parts are must. Even for the synchronous machine also same thing, whether it is motoring mode or generating mode or even transformer action also. Transformer action or motoring action or generating action, these parts are compulsory, these parts are must. Without the magnetic path and windings, you cannot design a machine. Now how to use this, how to use these parts, or what is the purpose of these parts, we will look into it one by one. Okay. All right. So let me show you here. Let me give you some information here. We have seen the different types of machinery like transformer, induction machine, DC machine and synchronous machine, right. All these machineries are operating on electrical energy maybe, or all these machineries are converting the other form of energy into electrical energy. Transformer is converting electrical energy into electrical energy only. It's not converting actually, it's just transferring from one side to another side. Induction machine, induction motor, it converts the electrical energy into mechanical energy. Induction generator can convert the mechanical energy into electrical energy. And for the DC motor, DC generator, synchronous motor and synchronous generator. Okay. So here coming to the energy conversion, we are discussing about the electrical machinery. So I just wanted to tell you about electrical energy popularity. Okay. The electrical energy is much more popular than any other forms of electrical energy. Okay. We have so many energy forms like mechanical energy, solar energy, wind energy, tide energy, like that so many energy forms are there. But electrical energy is very much popular, and hence the electrical machineries are popular. Okay. So electrical energy is popular because of few reasons. That is, generation is easy, and second one is transmission is easy, third one is distribution is easy, fourth one utilization is easy. Okay. Like generating the mechanical energy, generating the wind energy, generating the tidal energy is a little bit difficult. Even though you generate mechanical energy, transmitting the mechanical energy from one point to another point, okay, for over a long distance, if you assume over around 100 kilometers, if I have a mechanical energy here, for example, if a fan is rotating at this point, now I wanted to operate one more fan after 100 kilometers distance. Okay, what should I do? I should connect a shaft. Now connecting a shaft in a straight manner and rotating it, if the fan is rotating here, and if you want to rotate the other fan at 100 kilometers, it's a very difficult thing, because transmitting the mechanical energy till 100 kilometers is very, very difficult. So much of shaft losses will be there, rotational losses will be there. If you have wind energy, if you have wind at a velocity of around 100 kilometers per hour, and I wanted to transmit to till Coimbatore or otherwise Chennai with the same 100 kilometers, is it possible? With the same velocity? Not possible. Tide energy, it is available in the only oceans. So you will not get every tide, you will not get the same wave, no, same intensity, no. Okay. So whatever the energy forms you take up, the forms of energies are not efficient at all the stages. Like if you have a good form of energy at one stage, after transmitting over a longer distance, it may not be efficient. Okay, it might be losing the intensity, it might be losing the, that is what it might be losing intensity, it might be losing the velocity and all those things. So that is the reason why here electrical energy is popular. Converting the mechanical energy into electrical energy is easy. Of course, you require a generator and construction, installation is other thing. Converting mechanical energy into electrical energy is easy. Generation of electrical energy is easy. And after generation, you can transmit over a longer and longer distances. Around 200 kilometers, 400 kilometers also you can transmit. After transmitting, distribution is easy. Distributing the mechanical energy to the sub parts is very tough. Because if you see any mechanical vehicle, bus, okay, if you want to distribute the mechanical energy between the two tires or between the front wheels and back wheels, you need a gear mechanism box. Huge losses will be there. But when it comes to distribution, just place a wire or just place a conductor. It will be easily distributed. Division of electrical power, electrical energy is very easy. And similarly, at the last point, utilization. Utilizing the electrical energy in the form of light, in the form of mechanical, in the form of heat, whatever the form. Electrical energy can be converted into light energy, heat energy, and mechanical energy, whatever the form you want to convert. Conversion is easy at the utilization point, at the customer point. Okay, and along with this, at all stages, controlling is very, very easy. Controlling is very easy, I can say. How? Just by closing the isolator and opening the isolator, you can disconnect the transmission line or connect the transmission line with respect to generator, even with respect to distribution lines also. At the utilization point, you just switch on, switch off. You can stop the light, you can switch on the light. Controlling switching off, switching on process is very, 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 very easy. If you think about mechanical energy, if some mechanical body is running and if you want to stop it, you need to apply a brake. The moment when you apply a brake, it will not stop. It will take some time. Even heat energy also, if you switch off, like if you want to decrease the temperature, it will take some time. If you want to increase the temperature, it will take some time. But electrical energy is very quick at any point of time. If you just disconnect, connect. Very easy to control. That is the reason why electrical energy is very much popular. Electrical energy is very much popular and electrical machinery is also popular. Because use this electrical energy and try to convert into any form of energy. If you want mechanical energy, convert into mechanical energy. If you want to convert electrical energy into mechanical energy, use the machinery. And that is what here at this point. If electrical energy is so much popular, then how to generate it? How to generate it? How to generate or how to create electrical energy? How to generate or create electrical energy? Here comes the Michael Faraday. Michael Faraday has proposed two ways. Michael Faraday has proposed two ways. Okay, how? Use magnetic path and conductors. Those two paths are must. Okay, use magnetic path and conductors. Those two paths are must. And between them, you try to create some relative motion. You try to create some relative motion. We will see what is relative motion. Okay, that is what he said. How to generate electrical energy? Michael Faraday has proposed the ways. Faraday has proposed the two ways. Okay, what are the two ways? One is stationary induced EMF method, another one is dynamically induced EMF method. I am repeating, one is stationary induced EMF method, another one is dynamically induced EMF method. Okay, I am not saying first one is stationary induced EMF, first law is stationary induced EMF, second law is dynamically induced EMF. Actually, dynamically induced EMF method is the first law of Faraday and stationary induced EMF method is second law of Faraday. Okay, let me write first law here. First law is dynamically induced EMF or speed induced EMF. Okay, we can also call it a space varying induced EMF. And the second law is stationary induced EMF or statically induced EMF. Stationary induced EMF or statically induced EMF. So he has proposed these two ways. Let us see here, let us see the ways of generation. Okay, so whatever the listed, I have listed. Induced EMF, how to generate the EMF. There are two ways, stationary induced EMF and dynamically induced EMF. In the stationary induced EMF, we will be getting self-induced EMF and mutual induced EMF. Okay. So, as I am going to discuss first transformers, I will be discussing about stationary induced EMF, and in the rotating machines, that is DC machines or induction machines, there I will be discussing about dynamically induced EMF. Okay. If possible, I will try to add one question in between for the dynamically induced EMF also. Okay. So this is, these are the two ways to generate the EMF. Let us move on to the methods, that is self-induced EMF, that is self-induced EMF method. We will try to start with the self-induced EMF method. As I said, it is proposed by Faraday. Faraday has proposed like this. If you want to convert mechanical to electrical or electrical to mechanical, two parts are must, magnetic path and windings. Now here, what actually the magnetic path will do? Magnetic path carries the flux lines. Okay, so magnetic path carries the flux lines or establishes the flux lines, right? And the second part, winding, or you can also call it as conductors. You can call it as conductors. Now what these conductors will do? Conductors will carry the current, or conductor, inside the conductor EMF can be generated. Or conductors can carry the current. Okay. So I said there are two magnetic paths and two windings. If it is a transformer, only one magnetic path is there and two windings are there. Only one magnetic path is there and two windings are there. So why two windings are there? Why not only one winding? Because here, see, magnetic path purpose is to carry the flux lines. Who will produce the flux lines? There are two sources. The flux lines can be produced by the help of permanent magnet, and electromagnet. Flux lines can be produced by the help of permanent magnet and electromagnet. Here, permanent magnet is just phi, and electromagnet flux I can take up it as phi of t. This is time varying. And the permanent magnet flux is time invariant. Okay. So this field, if you use permanent magnetic path, that is, if the magnetic path used in the machinery is a permanent magnetic path, the flux establishment is on its own, it will be developed and it doesn't change with respect to time. That's why I have written it as time invariant. Okay, right. If you use permanent magnet, what will happen? Generally, if you want to generate the EMF depends upon the quantity we are going to use, that is flux we are going to use. So if the EMF depends upon flux, or otherwise if the mechanical energy depends upon the flux, you cannot change the flux value if you use permanent magnet. You cannot change the flux value. Therefore, the output also cannot be changed. Okay. So if you want to control the output value, it is better to it's better to have as many controls as possible in our hand. That's the reason why I am repeating this once again. If you want to control the output, it's better to have as many controls as possible in our hand. It's better to have as many control variables as possible in our hand. If you use permanent magnet, you cannot change it. If the permanent magnetic flux cannot be changed, output also cannot be changed. That's the reason why use of permanent magnet in all the machines, all the popular machines, whether it is transformer, DC machine, synchronous machine, induction machine, you cannot see that. You cannot see them in bigger size, larger size. But portable machines will use permanent magnets because the output is less, so no need to have a control. As we can't have a control over the permanent magnetic field, we don't use. So electromagnet is popular. Electromagnet is nothing but what? Electromagnet is nothing but here like this. We will be having a magnetic path, can be a steel, iron, or different types of magnetic materials are there, right? On that magnetic material we will be placing the winding like this, number of turns, and the winding is connected to an alternating voltage source or else a direct current source. So whenever you give a supply, it's a time varying voltage. If you give an alternating voltage source, an alternating current flows, and this alternating current creates an alternating magnetic field. The magnetic field direction will be according to right hand thumb rule. We will explain in detail later. So this is the time varying magnetic field. Okay, I am saying about electromagnet and that to phi of t. If you want to get time varying magnetic field, current must be time varying. If you want to get current as time varying, source, applied voltage source must be time varying. There is another possibility also there. The same magnet, that's the same magnetic path if you take up, okay, same magnetic path or maybe a steel or any material, and I am placing the winding here, and now you can connect a DC source. If you connect a DC source, it's a constant voltage source. This constant voltage source will drive a constant current through the winding, and the constant current will create a flux again. And this flux is time invariant. If you don't use permanent magnet, you can use electromagnet also. This is also electromagnet, this is also electromagnet. Electromagnet means here simply this winding is producing a current, this current carrying conductor is producing a flux lines. As a flux is emitting from this side, it's a north pole and this is like a south pole. Here also this is like a north pole and this is acts like a south pole. So this part is acting like a magnet. Why? Because of electric supply. That's why it is called as electromagnet. Okay, you can have time invariant electromagnet, time invariant magnetic field and time varying magnetic field. This is different from permanent magnet again. In the permanent magnet we don't use winding. We don't need an excitation. Permanent magnet doesn't need an excitation. Here we need an excitation. Still here you can change. If you put a potential divider, okay, let me erase this. If you put a potential divider like this, and if you change the tapping on this, the voltage applied across the winding will be changed and hence the current changes, therefore the flux changes. The flux can be 1 Weber, 2 Weber, 3 Weber and so on. Flux is not changing with respect to time, flux is changing with respect to voltage applied voltage magnitude. Okay, so here the flux magnitude changes if you change the voltage input. Here the flux magnitude is changing according to time by the nature of source. Here the nature of source is time invariant, here the nature of the source is time varying. So it's automatically changes, but this until unless you change the tapping, you cannot get the change. So we can use this electromagnet or this electromagnet. Whenever you want time varying magnetic field, you use this one. Whenever you want time invariant magnetic field, you use this one. But don't try to use a permanent magnet, because if you use a permanent magnet, you will lose the control. Here we are able to control the flux now. If you control the voltage, if you control the tapping, you can control the flux. If you control the flux, you can control the output. So I can just put a point together, I am repeating. Magnetic path carries flux lines. The flux lines you can choose it from permanent magnet or electromagnet. We don't choose permanent magnet because it gives you a constant magnetic field. We cannot change it. Therefore, we choose electromagnet, and electromagnets are of two types again. One is AC energized, another one is DC energized. Here AC energized, if it is AC energized, it's time varying magnetic field. If it is DC energized, it's time invariant magnetic field. If you want to get change in magnitude, you can change the tapping, or if you can change the potential divider so that flux can be controlled. Alright, so that is about the electromagnet. and that's about electromagnet, time varying and time invariant. So this is time invariant, okay, and this is time varying flux lines. And the second part is winding or conductors. I said two windings we will be using in each and every machine, whether it is transformer, DC machine or any machine, two windings. You see, out of two windings, this is one winding. Out of two windings, this is one winding. Okay, so one winding purpose is in any machine, one winding purpose is to create the magnetic field. One winding purpose is to create the magnetic field, and the other winding purpose is to create the energy, electrical energy. Okay, so winding one purpose, I am just giving a number randomly, winding one purpose or one winding purpose is to create the magnetic field, because for energy conversion magnetic field and conductors are must. How to create the magnetic field? Use an electromagnet. What is an electromagnet? A magnetic path over a coil excited with an electric supply, that's an electromagnet. So out of these windings, one winding is going to create the flux, one winding is going to create, winding 1 creates the flux and winding 2 creates the EMF now. Because we are discussing about methods of generation, na? We are discussing about methods of generation of electrical energy. How to generate? So use these two parts. EMF can be generated. Now let me show you. I have designed one part, that is magnetic path. Magnetic path is finished, over which one winding is also finished. Now next part is what? Another winding part is available. Another winding part should be discussed here. Okay. So I am taking here a time varying magnetic field. I am not taking this time invariant magnetic field. I am not taking time invariant magnetic field. I am taking time varying magnetic field. So let me go ahead with the time varying magnetic field. If I take up time varying magnetic field, it will be like this. If I take up time varying magnetic field, it will be like this. On this is a magnetic path, rectangular magnetic path. On this rectangular magnetic path, I am placing some turns, okay, and I am giving an alternating voltage source. This alternating voltage source is going to drive a current like this. For time being, I am taking positive polarity here. So alternating voltage source is going to drive a current like this. You can find the direction of flux lines by applying right hand thumb rule. Let me explain about right hand thumb rule. Right hand thumb rule says like this. Right hand thumb rule, right hand thumb rule will be like this. There is a right hand and thumb. Okay. Thumb indicates current direction. Thumb indicates current direction and closed fingers will indicate flux direction. These are closed fingers or curved fingers, curled fingers will indicate flux direction. This is the right hand thumb rule for a straight conductor. Right hand thumb rule for a straight conductor. Okay. Right hand thumb rule for straight conductor. Okay. So if you, let me show you one question here, a simple question. I have a straight conductor. I have one more straight conductor. This straight conductor is carrying a current in the upward direction and another straight conductor is carrying a current in the downward direction. Another straight conductor is carrying a current in the downward direction. Then what is the flux direction produced by these current carrying conductors? If this conductor is straight here and the conductor is carrying the current in the upward direction. So apply now right hand thumb rule. Current is going upward. So therefore the flux produced is going to be indicated with the curled fingers. This curly fingers. Okay. So it looks like anti-clockwise for us. Okay. Current is going upward. You treat me as a conductor and the current is going upward. So the flux lines produced will be around me, it will be like anti-clockwise. it will be around like anti-clockwise. Okay, so this is flux direction. If the current goes downward, then the flux direction will be clockwise. If the current goes downward, then the flux direction will be clockwise. These are the flux directions for a straight current carrying conductor. But when it comes to here, this is not straight current carrying conductor. This is turns. Front side we are seeing like this, back side the current goes in the backward direction. Front side it is going from left to right. Back side it will go from right to left. Front side left to right. The current is moving from left to right, and back side it will be from right to left. So it is like a turn or a circular conductor. These are not straight conductors. These are circular conductors. So for circular conductors, the right hand thumb rule is quite reverse. Okay, I am writing here, instead of straight conductor, if the conductor is circular, here I have shown with a white sketch, you assume the white mark as circular conductor. Okay, the white mark as circular conductor. Instead of flux, it will be a current. Instead of current, it will be a flux. That's it. Okay. So white conductor, the circular part is conductor now, circular conductor. So let me write here, or let me show you here. If it is possible, I will show you here. This is circular conductor, and which is carrying the current in the anti-clockwise direction. Okay. That means what? We should indicate the current with the curled fingers. For circular conductor, curled fingers will indicate current. Okay, so the current is moving in the anti-clockwise direction. Therefore, the flux produced is upward. Like this. Okay. Now similarly, if I take up circular conductor, and in this circular conductor, if the current is moving in the clockwise direction, now I have to indicate like this. The current has to be indicated with the curled fingers. So current is moving in the clockwise direction. So the flux will be downward direction. Current is here, I can write flux. Okay. So it will be, the flux will be downward direction. It's quite opposite. Instead of indicating the current, you just indicate flux. Instead of indicating with the flux, you just indicate with the current. Okay, quite reverse. Okay, if you remember straight right hand thumb rule for straight conductor, you just make it opposite. Okay. Now, if you come here, if you can find out the right hand thumb rule, if you can apply the right hand thumb rule here, you will get the flux lines direction. You see, the current is moving from left to right, so current direction is indicated with the curled fingers because it is a circular conductor. For circular conductor, closed fingers or curled fingers will indicate current. Okay, so I am indicating current direction. Now thumb will indicate flux, so it will be upward. So I can list out here, I can represent the flux line in this manner. Okay, so this is the flux lines phi of t. As the flux is emitting from this side, it can act like a north pole and this can act like a south pole. Of course, you will be having a closed loop field. Like this. I am not indicating the closed loop fields, but for time being I am just indicating the flux lines like this. And it varies with respect to time. How? Whenever the voltage is minimum, current is minimum, flux is also minimum. Okay, here the flux is proportional to current and current is proportional to voltage according to Ohm's law. Okay, according to Ohm's law. If the voltage increases, current increases, also flux also increases. If the voltage decreases, current decreases and the flux also decreases. So this is a time varying flux lines. It can be 0 Webers, 1 Weber, 2 Weber, 3 Weber and maximum value. Maximum value again it will come down to, if you assume the maximum value as 5 Webers, 5, 4, 3, 2, 1, 0, it will come down. That's how it changes. Okay. Now one winding part is done and magnetic path is also done. Magnetic path is also done. Next I have to place another winding. Next I have to show you another winding. So let me show you here another winding. Instead of showing you another winding, what I am trying to show you is just I am placing a piece of conductor. I am not placing so many turns here. I am not placing so many turns here. I am placing a piece of conductor here. I am placing a piece of conductor. Okay. Right. I am not taking so many turns. In that turns, piece of conductor I am taking. Now if I place this winding, or if I place this piece of conductor near to the flux lines or in the presence of flux lines, what will happen? Obviously, there will be chance of linkage of flux lines with respect to conductor. There will be chance of flux lines linkages with respect to this conductor. What are there inside the conductor? We have free electrons inside the conductor. We have free electrons inside the conductor. Okay, so many free electrons are there. So many free electrons are there, existed randomly. At room temperature, 10 to the power of 23 to 10 to the power of 28, free electrons will be there. Free electrons will be there. They are detached from the atomic structure. Okay. Now, if I place that kind of conductor, just one cube of conductor consists 10 to the power of 23 to 10 to the power of 28. Only one cube, 1 meter cube. Okay, right. You just imagine this much of length of conductor consists so many crores of free electrons. All right. Now, if I place this conductor near to the flux lines, and now this flux line is linking, the flux line is establishing like this. While the flux line is establishing, the flux line is cutting the conductor or linking with the conductor. And therefore, what happens? Please try to understand this point very clearly. Flux lines is interacting with the electron field, the imaginary field around the electron. If I have an electron, we'll be having an imaginary field around it, right? And the flux line is going to interact with this one. The flux line is going to interact with this line. So, whenever the external magnetic field is interacting with the conductor, definitely it interacts with the imaginary field over the electron, and therefore there might be chance of creation of force of attraction or force of repulsion. Between these two flux lines and electron, there might be chance of creation of force of attraction or force of repulsion. That force of attraction or repulsion, what it will do? If attraction force is created, the electron will be attracted. If repulsion force is created, the electron will be repelled. On the whole, the electron is energized. So, on each and every electron, a force is created. A force is created. On each and every electron, a force is created. What does it mean is, on each and every electron means, not all the electrons. On few electrons, let me correct myself, on few electrons, a force will be created. So, here, this force we call it as electromotive force. Okay, a force which moves the electron. Please try to understand this point. A force which moves the electron, we call it as electromotive force. Okay, right. Here the flux line is changing, na? Here if the flux line changes, if the flux line is 1, it might be creating the force on 4 to 5 electrons. If the flux line is increasing, it might be creating the force on few more electrons. If the flux line still increases, the force on the electrons will be number of electrons can experience more number of electrons can experience force, more force. Okay, it is like the number of linkages. He said that if the flux linkages are more with respect to time, then the electromotive force is also more. If the more number of flux linkages are, if the more flux lines are linking with the conductor, then force induced on each and every conductor is also more. If flux lines linkages are less, then induced EMF is also less. That is what he said. The rate of change of flux linkages with respect to conductor is directly proportional to EMF induced in that conductor. What is that force? Electromotive force. I am just representing with E. Okay. I am repeating once again. Give a supply, it drives a current, produces a flux, and that flux can link with the neighboring conductor, and the neighboring conductor has so many free electrons. On that free electron, a force can be experienced because of imaginary field of the electron and external field of this magnet. Between those two fields, a force will be created on the electron because electron is free. So you can experience a force on it. That force can be attraction force or repulsion force. We call it as electromotive force. Okay. Earlier the electron is not energized, and now the electron is energized. It is ready to move now. So a force will be created on the electron, and that force can move the electron from one place to another place whenever you give a closed path, whenever you provide a closed path. So this force depends upon what? Will you get force on each and every electron? No. Will you get force on each and every electron in the conductor? No. The force on the electron depends upon the ability of the flux lines or the strength of the flux lines linking with the conductor. If I have just 5 flux lines linkages, 5 flux lines might be having an impact on 5,000 electrons, maybe 5 lakhs electrons only, but not on crores of electrons. I am repeating, if I have flux lines linkages of 5, these 5 flux lines linkages can create a force on maybe 5,000 electrons. Maybe 5 lakh electrons, but not complete electrons, but not all the electrons. Because the flux line is also having ability now. Every quantity will be having some ability strength now. So these flux lines can create only on certain number of electrons. So that is what EMF, the electromotive force created on the electron depends upon the rate of change of flux linkages. The rate of change of flux linkages. So we have to discuss about this part very much clearly. We have to discuss this electromotive force is depending upon rate of change of flux linkages very clearly. Let me tell you on a new slide. As I said, electromotive force is depending upon E is proportional to d psi by dt. Okay, d psi is nothing but flux linkages. Okay, n into phi, flux linkages. All right. So I can write the EMF equation as n into d phi by dt. So EMF induction depends upon the rate of change of flux lines. What does it mean? Please try to understand. If I have an alternating magnetic field like this, phi of t, maybe this maximum value is 5 and the minimum value is 0. Okay, so it is changing the value from 0 to 5. 0, 1, 2, 3, 4 and 5 is the maximum value, and then again it comes down to 5 to 0. So it goes on according to time. Now this kind of flux line is linking with the conductor. So let me show you the conductor again. Okay, here is a conductor. On this conductor, so many electrons are there here. Free electrons. Now what I am saying here, if I take up certain instant called instant 1, and at this instant 1 the flux lines are 2 Webers. Initially at 0 instant no flux lines. That means what? The flux lines linking with the conductor is not, there is no flux lines linkages. Okay. Now from 0 to 1 instant there are 2 flux lines linking. Now let me show you 2 flux lines linking. Okay. Earlier no flux lines linkages and hence no force on the electrons. and now two flux lines are linking. So compared to previous case from 0 to 1, the change is 2. And therefore, now these two flux lines will create an impact on few amount of electrons, few number of electrons. Out of crores of electrons, out of so many crores of electrons, these two flux lines will create only on few number of electrons, maybe 2000 electrons, let us assume. Okay, so 2000 electron groups can be, what I can say, 2000 group of electrons can be energized. 2000 group of electrons can be energized, maybe like this. Okay, I'm just telling that these group of electrons are around 2000 number of electrons. All right, so these two flux lines has created a force on the 2000 electrons, and remaining rest of electrons doesn't have any force, because the ability of the two flux lines is just 2000. The ability of the flux line is to create a force only on 2000. It cannot create force more than it cannot create the force on more than 2000 electrons. Okay, now if the two flux lines are constant, so these two flux lines are constant, therefore force is created on the 2000 electrons already. That's it, done. No more force, no more new force is going to be created. No more new electromotive force is going to be created. Okay, so these two flux lines can create a force on 2000 electrons. Okay, after this, if these two flux lines are constant, you cannot get a force on other than 2000. Its ability is finished now. It cannot pull, it cannot attract or repel other than 2000 electrons. If you want force, or if you want electromotive force continuously, if you want to get electromotive force continuously, then the time, according to the time, the magnitude has to change. It might be 4. Okay, if this changes, maybe at this instant, 2-second instant, or any instant. Okay, if the time changes, according to the time, if its magnitude also changes, now 2 flux line has become 4 flux line. Now this time, here, this time, okay, let me take up 4 flux line. This time the electrons created maybe 10,000 electrons. Okay, maybe the 4 flux lines is going to create the force on 10,000 electrons. Okay, so 4 flux lines are going to create the force on, let us assume, 10,000 electrons. So these 10,000 electrons are getting energized, electromotive force is generated on it. If you close the path, it is ready, the electrons tries to move, ready to move, otherwise not. Now 4 flux lines are constant. If 4 flux lines are constant, 10,000 electrons, let us assume 10,000 electrons are attracted. No more extra electron is going to be attracted. No more EMF is going to be induced. No more EMF is going to be generated. If you want to get continuous force on the electron, there must be a continuous change on the flux lines. So if it goes to 5, and according to 5, then the electrons will be maybe 12,000 electrons, or 14,000 electrons can be energized or attracted or repelled. If the phi is constant, if the 5 flux lines linkages are constant, only 15,000 electrons will be, 15,000 or 14,000 electrons will be attracted, and after that, if the 5 flux lines are constant, no more electron is going to be energized. I am repeating again and again because it is very, very important. I wanted to say one point, that if the flux lines linkages are constant, no more extra force is going to be created. No more extra force is going to be created. Continuously the flux lines linkages has to change. Then only continuously the force on the electrons also changes. Continuous generation of EMF is possible. That is what? E is directly proportional to d psi by dt. As long as the flux linkages changes with respect to time, of course, as long as the flux linkages changes with respect to conductor, of course, there is a conductor. Flux lines has to link with the conductor. Na? If you treat the cheek as conductor, flux lines as my hand fingers, 1, 2, 3, 4. Okay, if only one flux line is linking, the moment when it link with the cheek, you will get a pain. The moment when you hit with the finger, you will get a pain. If the finger is like that, you will not get a pain. Now the second finger comes and hits, you'll get a pain. If the two fingers are like that, you'll not get a pain. When the third finger comes and hits, you'll get a pain. If the three fingers are like this, you'll not get a pain. So as long as it changes, the pain induces. So EMF is like a pain. EMF is like a pain. And the flux linkages is like a hitting process or slapping process. Flux linkages is like a slapping process. Okay. Remember, flux linkages is like a slapping process. Right, I am repeating again and again. The rate of change of flux linkages is proportional to EMF induced. So as long as the rate is there and the flux linkages with respect to conductor is there, EMF will induce continuously, a force will induce continuously on the electron. If flux lines are constant, EMF is 0. Okay. So that is what even you say here, if d phi by dt is constant, if d phi by dt is constant, then EMF is 0. If you want to get electromotive force or if you want to generate the electrical energy, there must be a change in linkage of flux lines with respect to conductor. There must be a change in linkage of flux lines with respect to conductor. Otherwise, EMF will not induce. Let it be any way. Whether it is dynamically induced EMF or stationary induced EMF, doesn't matter. There must be a change in linkage of flux lines with respect to conductor. Otherwise, EMF will not induce. If the flux linkages are constant, EMF will not be induced. If the flux linkages are changes, if the flux linkages are constant, EMF will not induce. If the flux linkages are changes continuously, EMF will induce. Okay. So that is what about the induced EMF. Here, why are we calling it as stationary induced EMF? Why are we calling it as stationary induced EMF? Because conductor is stationary here. Conductor is stationary. As a conductor is stationary and EMF is inducing on the electrons, we call the induced EMF as stationary induced EMF. We call the EMF as stationary induced EMF. Okay. I am writing EMF is stationary induced EMF. Why? Because the conductor is stationary and the force is created on the electrons which are existed in the stationary conductor. That's why you are calling it as stationary induced EMF. And we will see in which direction the EMF will induce, or the polarity of induced EMF, we will see after a question. Let's have a discussion. Let's take up a question so that we can understood in a better manner. Okay, right. Look at this question. The total flux at the end of a longer bar magnet is 500 microwebers. The end of the bar magnet is withdrawn through a 1000 turn coil in 1/10 second. In 1/10 second. The EMF generated at the terminals of the coil is, the EMF generated at the terminals of the coil is. Okay. He has given flux lines, he has given number of turns, he has given time also. What do we know so far? We know EMF equation. He is asking EMF only. So if you take up EMF equation can be taken as N into d phi by dt. We know N, this is 1000 turns. He has given the flux lines at the end of the bar magnet and he has given the time also. We have to calculate change in flux lines and change in time. Okay. According to this data, if you look at the diagram will be looking like this. A longer bar magnet. See, you assume these number of turns as 1000 turns. Okay, the number of turns as 1000 turns. Let me take up the number of turns are here 1000 turns. Okay. Now this 1000 turns, from this 1000 turns I am removing a bar magnet like this. Here, this is the bar magnet, right? There is a bar magnet. This is the bar magnet. Okay. So we are withdrawing the bar magnet completely. At the end of the bar magnet, he said that the flux lines are around 500 microwebers. At the end of the bar magnet, the flux lines are 500 microwebers. Okay. When the bar magnet is inserted in the coil, all these flux lines are cutting, all these flux lines are linking with the turns. You see, all these flux lines are, this flux line is cutting this first turn, second turn, third turn and fourth turn, and till 1000 turns it will cut. Flux line is linking with the turn. Flux line is linking with the turn. We call it as flux linkages, n into phi. N into phi. Okay. So with 1000 turns it will cut. With the 1000 turns it will have a flux linkages. And now what I am doing, and I am completely removing the entire bar magnet. If I remove the bar magnet, it will look like this. I have a 1000 turn coil. Now if I remove the bar magnet outside, the bar magnet is here, north pole and south pole. Can you tell me what are the flux linkages with respect to conductor now? Earlier 500 microwebers are linking, and now the flux linkages are 0. Earlier how much flux linkages here? The flux linkages are 500 microwebers. Now the flux linkages are 0. Now I can take up the change in flux lines. The change in flux lines are going to be, let me take up just phi only. Okay. Now the change in flux line is going to be phi 2 minus phi 1. Okay. Phi 2 is 0, phi 1 is 500 microwebers. Phi 1 is 500 microwebers. Okay. So this is my change in flux lines. We can write it as d phi. Okay. So in the formula we have got d phi by dt. d phi by dt. So d phi information I have got. Okay. So let me substitute here. N is 1000 turns and d phi is of 0 minus 500 microwebers and divided by dt. Okay. So what is dt? He said that the end of the bar magnet is withdrawn through 1000 turn coil in 1/10 second. Okay. If I start pulling it in just 1/10 of second, I just removed it completely. So change in time is what? T2 minus T1. I just pulled it in T2 seconds, in a time of 1/10 second. So I can write the dt is equals to T2 minus T1. If initial time is 0, then next time you can take up it as 1/10 minus 0. You substitute 1/10, that's it. Okay. So if you substitute 1/10 second here, then you will get the answer. Can you tell me what could be the answer here? 500, 10 to the power of minus 6 and this 10. If this 10 goes up, it will be 10 to the power of 4. 10 to the power of 4 into 500 into 10 to the power of minus 6. So 10 to the power of 4 and 2 zeros are there, 500. 10 to the power of 6. So 10 to the power of 6, 10 to the power of 6, 10 to the power of minus 6 gets cancelled and you will get minus 5 volts. But here we take up only magnitude. So if you take up magnitude, the answer will be, you will get A, 5 volts. Right? So that is what the stationary induced EMF. Here the conductor is, winding is, I can say here the winding is stationary, number of turns are stationary, and we are changing the time. By the way, this flux is not time varying. We are changing we are pulling it, and according to it, changing. According to the pulling action, according to moving action, the flux linkages are changing, and hence EMF is inducing. Okay, right. So, but whatever the discussion we had so far, to get a stationary induced EMF, time varying magnetic field is there. Okay, but in the question what we have taken, it's not time varying magnetic field, it's permanent magnetic field, but we are changing that flux by moving action. Okay, so remember, you try to understand whether it is either you should have a time varying magnetic field or otherwise make the flux as varying by moving action or by mechanical action. Then only you will get EMF. Otherwise, if you don't get rate of change, if you don't have a flux linkages change, you will not get a EMF. Because of movement action, you are getting a flux linkage change and hence EMF is inducing. Otherwise, you don't get. Don't think that as a permanent magnet is there, so flux doesn't change and EMF will become 0. So don't, EMF is not 0. EMF is not 0. Anyhow, in the options he has not given EMF. If 0 is given, 0 is not the answer. Because of moment action, because of moment, definitely flux linkage will change and hence EMF will change. EMF will induce. Okay, that's it about the problem on the stationary induced EMF. And in the next session, we will be discussing about the polarity of induced EMF and the Lenz's law, and then we will move on slowly into the subject. Okay, all right, thank you.